What if a memory, the most private and intangible thing you own, is not truly yours? That recollection of a first kiss, the scent of summer rain on hot pavement, the precise shade of a loved one's eyes, they feel deeply, unshakably real. They exist within the three-dimensional architecture of your mind, inside a three-dimensional world of substance and depth of cause and effect. This is the reality you navigate every moment of your life, a grand theatre of height, width and breadth governed by the relentless forward march of time. You can reach out and touch the solid world, feel its texture, its weight, its reassuring presence. But what if that reassurance is the grandest illusion of all? What if the very fabric of existence, from the atoms in your hand to the most distant quasar burning at the edge of time, is a phantom, a beautiful, intricate, and impossibly convincing projection with all its seeming depth and volume cast, from a flat two-dimensional surface impossibly far away? Imagine your entire life, every thought you've ever had, every star we have ever charted being nothing more than a complex hologram. This idea sounds like a fever dream, the desperate scribblings of a forgotten mystic, yet it has emerged from the bleeding edge of theoretical physics, from the cataclysmic realm of black holes and the maddening paradoxes of quantum mechanics. It is a concept so profound, so utterly alien to our senses, that it forces us to question the very meaning of here and real. This is the holographic principle, a candidate for a final theory of everything, and it suggests that our universe is not at all what it seems. It whispers a cosmic heresy that we are the ghosts in the machine, figures of light and shadow playing out our lives on a stage that has one less dimension than we thought. To even begin this journey, we must first unlearn what we know. We must look again at the cosmos we thought we understood, not as a collection of objects, but as a repository of information. Think of the sheer staggering volume of it all. The universe appears to us as an infinite library, its shelves groaning under the weight of three-dimensional tomes. Each galaxy is a chapter, each star a sentence, each planet a word, and every particle, every quantum fluctuation, a single indispensable letter. We've spent centuries learning to read this book, decoding the light from ancient suns, translating the gravitational whispers between worlds. We have charted the great cosmic web, a celestial nervous system of galactic clusters, connected by filaments of dark matter stretching across billions of light years. Within this structure, we find breathtaking complexity. Here in the Carina Nebula, we witness stellar winds like a sculptor's violent chisel carving vast caverns out of glowing hydrogen gas. We see pillars of dust light years tall acting as cosmic incubators for generations of stars yet to be born. The depth is palpable. We can almost feel the parallax, the sense of one star cluster sitting in front of another, separated by an abyss of interstellar space. Then we pull back further and further until the nebula is just a bright smear in the arm of our own Milky Way, a spiral staircase of 100 billion suns. Our galaxy itself is just one of many in the local group, a small neighborhood of cosmic islands all gravitationally waltzing through the void. Beyond that lies the Virgo supercluster, a truly colossal gathering of thousands of galaxies, a metropolis of light and gravity whose scale defies human comprehension. And even this is just a single node in the incomprehensible network that constitutes the observable universe. Everywhere we look, we see a universe of volume. Space isn't just a backdrop, it is an active participant, a dynamic stage that can bend, warp, and ripple. Albert Einstein gave us the language to describe this stage with his theory of general relativity. He revealed that space and time are fused into a single four-dimensional fabric space-time. Mass and energy tell this fabric how to curve, and the curvature of the fabric in turn tells mass and energy how to move. A planet orbiting a star is not being pulled by an invisible rope. It is following the straightest possible path through a region of space that has been warped into a gravitational valley by the star's immense mass. This is a profoundly three-dimensional concept. The sun's gravity extends outwards in all directions, its influence diminishing with the cube of the distance, a testament to the volumetric nature of our reality. Our entire physical intuition is built on this foundation. Every equation we use to send a probe to Mars, every model we build to understand the formation of galaxies, assumes that we live in a universe with three spatial dimensions. It is the bedrock of our cosmic worldview. And yet, a profound crack has appeared in this foundation, a crack that originated in the most bizarre and extreme locations in the cosmos, the pitch-black heart of a black hole. Black holes are where our understanding of the universe breaks down completely. They are gravitational monsters, points of infinite density, where the curvature of space-time becomes so extreme that not even light, the fastest thing in existence, can escape. They are the universe's ultimate prisons, surrounded by a one-way membrane called the event horizon. Anything that crosses this boundary, a star, a planet, an astronaut, is lost to the outside universe forever. Or so we thought. For decades, this was the accepted picture. But it concealed a terrifying paradox, a deep and unsettling violation of the most sacred law in physics. This law states that information in the universe can never ever be truly destroyed. It can be rearranged, scrambled, or hidden, but its fundamental essence must always be preserved. Think of it this way. If you burn a book, you might think the information within it is gone, but a physicist would tell you it isn't. The information has merely been transformed. It is now encoded in the chemical composition of the ash, the pattern of the smoke, the temperature of the surrounding air, and the specific wavelengths of light and heat that were radiated away. In principle, if you could meticulously gather every single one of those products and trace their history backwards, you could reconstruct the original book. The task would be monumentally difficult, perhaps impossible in practice, but according to the laws of quantum mechanics, the information is still there. It is a cornerstone of reality. Without it, the logical consistency of the universe unravels. But black holes presented a direct and terrifying challenge to this principle. When a book falls into a black hole, it crosses the event horizon and is crushed into the central singularity. The black hole's mass increases slightly, but all the intricate information that made up the book, the story, the author's intent, the complex arrangement of ink on paper, seems to vanish without a trace. It's not just rearranged, it's completely erased from our universe. This was the black hole information paradox, a puzzle that tormented physicists for decades. It created a civil war in physics, pitting Einstein's theory of gravity, which predicted the existence of these information destroyers, against the established laws of quantum mechanics, which insisted that information must be conserved. One of them had to be wrong. The first clue to solving this cosmic crime came not from a physicist trying to unify grand theories, but from a graduate student in the 1972nd named Jacob Bekenstein. He was pondering a simple question: what happens to the entropy of an object when it falls into a black hole? Entropy is, in simple terms, a measure of disorder or complexity. It's also intimately related to information. A highly ordered system like a perfect crystal has low entropy. A disordered system like a gas spreading out in a room has high entropy. The second law of thermodynamics, another sacred pillar of physics, states that the total entropy of a closed system can only ever increase. Things naturally progress from order to disorder. When an object with entropy like our book falls into a black hole, its entropy seems to vanish from the universe, seemingly violating this second law. Bekenstein proposed a radical solution. He suggested that a black hole must have an entropy of its own, and that this entropy must increase by at least as much as the entropy of the object it swallows. But where was this information, this entropy, stored? Logic would dictate that it must be stored within the volume of the black hole. The more you throw in, the more storage space you'd need inside. But Bekenstein, through a brilliant series of thought experiments, arrived at a conclusion that was completely insane. He calculated that the maximum amount of information a black hole could possibly contain was not proportional to its three-dimensional volume, as everyone expected. Instead, it was directly proportional to the two-dimensional surface area of its event horizon. Let that sink in for a moment. All the information about everything that had ever fallen into this cosmic abyss, entire stars, planets, civilizations, was not stored times inside times. The black hole's immense three-dimensional interior. It was somehow imprinted, encoded, and stored on its flat two-dimensional boundary surface. It was as if you discovered that a vast, sprawling city's entire library with millions of books could be stored not on the shelves inside the building, but as a thin layer of paint on its outer walls. This was a shocking, preposterous, and revolutionary idea. At first, it was dismissed by many, most famously by the great Stephen Hawking himself. But then, Hawking, in an attempt to prove Bekenstein wrong, performed his own calculations, incorporating the strange rules of quantum mechanics into the curved space-time around a black hole. What he found stunned the world of physics and eventually himself. He discovered that black holes are not perfectly black. Due to quantum effects at the event horizon, they leak a faint glow of radiation now known as Hawking radiation. And crucially, this radiation meant that black holes had a temperature, and if they had a temperature, they absolutely had to have entropy. When he calculated the exact value of that entropy, it matched Bekenstein's formula perfectly. The information was not stored in the volume. It was written on the surface. This was the first great tremor, the first piece of hard mathematical evidence suggesting that our understanding of space and information was profoundly flawed. It hinted that three-dimensional reality might be a kind of cosmic trick. If nature's most efficient information storage device, the black hole, uses a two-dimensional surface to store everything that we perceive as three-dimensional, could this bizarre principle apply to everything else? Could it apply to the room you're in right now? Could it apply to the Earth, the solar system, the entire universe? This is the question that gave birth to the holographic principle. It proposes that our entire universe itself could be a projection of information stored on some distant two-dimensional boundary at the edge of the cosmos. That distant surface, often called the cosmic horizon, would act like a celestial hard drive, and everything we experience, the feeling of motion, the illusion of depth, the vastness of space between galaxies, is just the 3D playback of that. 2D data. The universe in this view is a hologram. Not like the simple illusions you might see in a museum, but a perfect quantum-level projection where the laws of physics themselves emerge from a more fundamental two-dimensional code. This is the precipice on which we now stand. We are forced to confront a reality that may be fundamentally different from our perceptions, a world built not on substance but on information. Our quest, then, is to become cosmic detectives, to follow the clues left behind in the mathematics of black holes and string theory. We must journey from the event horizon of a black hole to the edge of the observable universe, seeking the screen upon which our reality may be projected. What we are searching for is nothing less than the source code of the cosmos. The answers will challenge not only our science but our philosophy, our sense of self, and our place in a universe that is far stranger and perhaps far more elegant than we ever dared to imagine. The stage is set for a revolution, one that asks us to throw away the solid ground beneath our feet and accept that we might be living inside the most magnificent illusion ever conceived. What if the most fundamental ingredient of our universe is not matter, not energy, but something far more ethereal? What if reality in its deepest sense is written in a language we are only just beginning to decipher? For centuries, physics was the story of things, of planets and particles, of forces and fields. It was a tangible pursuit, a quest to understand the physical machinery of the cosmos. But hidden within that machinery, a ghost has always lurked: the concept of information. It was long treated as an abstraction, a human invention for organizing our knowledge of the world. Yet a revolution was brewing, a quiet and profound shift in perspective that would ultimately challenge the very nature of space and time. This revolution didn't begin in the heart of a star or the fury of a supernova. It began with a simple, almost playful question pondered by a brilliant young graduate student in the early 1972, a question about a hot cup of tea. His name was Jacob Bekenstein, and he was working at Princeton under the legendary physicist John Wheeler. Wheeler himself was famous for coining the evocative phrase "it from bit," the radical suggestion that every it, every particle, every field of force, even space-time itself, derives its very existence from bits, from the answers to yes or no questions from pure information. This was a philosophical provocation, a powerful seed of an idea. It was Bekenstein, however, who would find a way to drag this abstract notion into the terrifying physical reality of the most extreme objects in the cosmos, black holes. He was captivated by their enigmatic nature, these gravitational prisons from which nothing, not even light, can escape, but he was also deeply troubled by them. They seem to represent a profound threat to one of the most sacred laws of physics, a law that governs everything from the steam in an engine to the expansion of the universe itself. This pillar of physics is the second law of thermodynamics. It is at its core a simple and unyielding statement about the universe's relentless march towards disorder. It tells us that entropy, a measure of hidden information, of messiness, of the number of ways you can rearrange something's internal parts without changing its outward appearance, can only ever increase. A pristine deck of cards, when shuffled, becomes disordered. An egg, when scrambled, can never be unscrambled. The arrow of time itself seems to be painted by this inexorable rise of entropy. So Bekenstein imagined his hot cup of tea. It is a system teeming with entropy, a chaotic dance of countless water molecules, each with its own position and momentum. It possesses a certain amount of heat, a certain amount of information locked away in its microscopic state. What happens, he wondered, if you drop this cup of tea into a black hole? From the outside, the result seems catastrophic for physics. The tea, along with all of its heat and all of its intricate information, simply vanishes. It crosses the event horizon, that silent one-way membrane that cloaks the black hole's singularity, and is lost to our universe forever. Its entropy, its contribution to the total disorder of the cosmos, has been erased from the cosmic ledger. The second law of thermodynamics, a rule that had stood unchallenged for over a century, appears to be flagrantly violated. It was an intellectual crisis in a teacup. For many physicists, the answer was simple: black holes were just special. They were exceptions, cosmic oddities that played by their own inscrutable rules. But for Bekenstein, this was deeply unsatisfying. He believed the laws of physics must be universal, that they couldn't simply break down at the edge of a gravitational abyss. There had to be an answer, a way to save the second law. His solution was both audacious and breathtakingly elegant. He proposed that when the tea falls into the black hole itself must somehow gain the entropy that was lost. The universe's total entropy doesn't decrease. It is merely transferred, hidden away inside this gravitational vault. This implies something astonishing: a black hole must have entropy. It cannot be a simple featureless object as classical physics suggested. It must possess an internal state, a staggering complexity hidden behind its veil of darkness. But how could you possibly measure the entropy of something you can't even see inside? Where would this information be stored? Bekenstein was wrestling with the very soul of a black hole, trying to find a place to write down its secrets. The obvious answer, the one that makes intuitive sense in our three-dimensional world, is that the information capacity of an object should be related to its volume. A larger library, a bigger hard drive, can hold more books, more data. A black hole with more volume should therefore be able to store more entropy. But this is where Bekenstein took a leap of pure genius that would echo through the decades. He remembered a peculiar property of black holes that had recently been discovered by a brilliant and fiercely competitive physicist named Stephen Hawking. Hawking had proven that in any interaction, from the collision of two black holes to one swallowing a star, the total surface area of their event horizons could never decrease. It always went up. The parallel was electric, impossible to ignore. On one hand, you had the second law of thermodynamics: entropy only ever increases. On the other, you had Hawking's area theorem: the surface area of a black hole's event horizon only ever increases. The two laws had precisely the same mathematical behavior. Bekenstein made the courageous connection: perhaps they were in fact the very same law. He proposed that the entropy of a black hole, the total count of all the information it has ever swallowed, is not proportional to its volume, but is instead directly proportional to the surface area of its event horizon. Think about what this truly means. Every star, every planet, every teacup that has ever fallen into the black hole leaves an indelible mark, not within the crushing depths of its three-dimensional interior, but somehow encoded on its two-dimensional boundary, surface. The story of its entire life, the complete catalogue of its contents, is not stored in the volume of the library, but is instead written like ghostly inscriptions upon its walls. This was the first glimmer, the first mathematical hint of a holographic universe. It suggested that a 3D volume of space could be fully described by information living on its 2D surface. a concept so profoundly counterintuitive that it bordered on scientific heresy. The idea was radical, and the pushback was immediate and severe. And the most powerful voice of opposition belonged to the very man whose work had helped inspire it, Stephen Hawking. Hawking was a titan of physics, a mind of unparalleled power who had dedicated his life to uniting the two great pillars of modern science: Einstein's general relativity, the theory of the very large, and quantum mechanics, the theory of the very small. He was convinced Bekenstein was wrong, and for a very specific reason. If an object has entropy, it must also have a temperature, and if it has a temperature, it must radiate heat, it must glow, even if only faintly. But the entire definition of a black hole was that nothing, absolutely nothing, could escape its gravitational clutches. They were the blackest things in the universe, the ultimate cosmic prisons. For a black hole to radiate would be a contradiction in terms. So Hawking set out with all the formidable mathematical firepower at his disposal to prove Bekenstein's beautiful idea was fatally flawed. He began to investigate the bizarre quantum effects that must occur right at the edge of a black hole's event horizon. He wanted to show once and for all that they were perfectly eternally black. In the quantum world, empty space is anything but empty. It is a roiling, seething foam of uncertainty, a place where pairs of virtual particles, one matter, one antimatter, are constantly popping into existence from borrowed energy, only to find each other almost instantly and annihilate in a puff of nothingness. They are ephemeral ghosts in the machine of reality. Hawking asked a devastatingly simple question: what happens if a pair of these virtual particles is born right on the precipice of an event horizon? In this precarious location, a strange fate can befall them. It's possible for one particle, say the antimatter particle, to fall across the boundary, while its matter partner is left stranded alone in the outside universe. The particle that fell in can never escape to annihilate its twin. The abandoned particle, now a real bona fide particle with positive energy, has no choice but to fly away into space. To an observer watching from a safe distance, it would look as if the black hole itself had just spat out a particle. It would appear to be radiating. It would seem to have a glow. Hawking was stunned. His calculation, which he had undertaken with the express purpose of demolishing Bekenstein's theory, had achieved the exact opposite. It had proven with the unyielding rigor of mathematics that Bekenstein was fundamentally right. Black holes do have a temperature, they do have entropy, and they do radiate. This faint, ghostly emission would forever be known as Hawking radiation. It was one of the most profound discoveries in the history of theoretical physics, a stunning marriage of gravity, quantum mechanics, and thermodynamics. For his part, Bekenstein was vindicated. His wild idea about information being stored on the surface was no longer a fringe speculation. It was now supported by the calculations of the greatest living mind in cosmology. It should have been a moment of triumph, a celebration of unity and progress. Instead, it was the beginning of a nightmare. It was the birth of a paradox so deep, so intractable, that it would threaten to break physics itself. The problem was hiding in the very nature of Hawking's spectacular discovery. His calculations showed that the radiation escaping the black hole was purely thermal. It was random, chaotic, and generic. It carried energy away, but it contained absolutely no information about what had fallen into the black hole in the first place. Imagine you have two books, a complete collection of Shakespeare's plays and a telephone directory. You throw both into a fire. The smoke, heat, and ash that come out are in principle fiendishly complex. But a sufficiently powerful supercomputer could, in theory, trace every particle backwards and reconstruct the exact pattern of ink on the pages. The information is scrambled, not destroyed. This is a core tenet of quantum mechanics, a principle called unitarity, which states that information about a system can never ever be truly erased from the universe. Now consider two black holes. Into one we throw Shakespeare's plays, into the other the phone book. Both black holes will grow slightly, their surface areas increasing according to the information they have consumed. Then, over immense, unimaginable timescales, trillions upon trillions of years, they begin to evaporate. They slowly shrink, bleeding their mass back into the cosmos as a faint drizzle of Hawking radiation. According to Hawking's original formulation, the radiation coming from both black holes is identical. It is a featureless thermal hiss. It carries no trace of sonnets or soliloquies, no memory of names or numbers. It is cosmic static. Eventually, after an almost infinite amount of time, the black holes radiate away completely. They vanish from space-time in a final, quiet puff of energy. And with them all the information they once contained, the intricate genius of Shakespeare, the mundane data of the phone book has been utterly and completely annihilated. This was the crisis. It became known as the black hole information paradox, and it created a chasm that ran right through the heart of modern physics. On one side stood Einstein's general relativity, which described the smooth, predictable geometry of space-time that allows black holes to form and swallow information. On the other side stood quantum mechanics with its unyielding law that information is eternal and indestructible. The two theories, our twin masterpieces of understanding, gave answers that were fundamentally irreconcilably different. They could not both be right. Physics had been brought to its knees. The paradox revealed a crack not just in our theories, but in our very conception of reality. Where did the information go? Does it leak out in some subtle way that Hawking missed? Is it hidden in a remnant, a tiny nugget of exotic matter left behind after the evaporation? Or is one of our most cherished scientific principles simply wrong? The search for an answer to this profound question would lead physicists down a rabbit hole of speculation into worlds of extra dimensions, string theory, and quantum gravity. It would force them to reconsider the very meaning of space, of time, and of existence. The paradox, born from a thought experiment about a cup of tea, had become a celestial blowtorch, burning away the certainties of the old world and illuminating the path toward a new and revolutionary idea. An idea that suggests the solid three-dimensional world you see around you might be nothing more than a projection, a grand illusion painted on a distant two-dimensional screen. The resolution to the crisis of lost information would not be found by looking deeper into the black hole, but by accepting the bizarre lesson it was trying to teach us, that perhaps in the deepest sense imaginable, our universe is a hologram. The paradox, once unleashed, had become a chasm cleaving the heart of physics. On one side stood the stately, unyielding pillar of general relativity, Einstein's grand vision of gravity as the elegant curvature of space-time, a world where the descent into a black hole was a smooth one-way journey into oblivion. On the other stood the frantic, probabilistic world of quantum mechanics, a realm governed by an unbreakable law that information, the fundamental essence of what makes a thing what it is, can never ever be truly destroyed. For 2 decades, this schism widened, a cold war fought in the hushed halls of academia and on the chalk-dusted blackboards of theoretical physics. Stephen Hawking's conclusion that black holes evaporate and take their secrets with them was not merely a puzzle. It was a declaration of war against the very foundations of quantum reality. The universe, it seemed, had a bug in its source code, an irreconcilable contradiction at its most extreme limit. Most physicists simply looked away, hoping the problem would resolve itself, a mathematical phantom that would vanish with a more complete theory. But for a few stubborn, brilliant minds, looking away was not an option. The contradiction was not a phantom. It was a signpost, pointing towards a truth about reality more profound and bizarre than anyone had dared to imagine. The confrontation was inevitable, and it would arrive not from a single unified front, but from 2 independent thinkers, separated by an ocean, each wrestling with the demon of information loss in his own unique way. From the Netherlands, a mind of formidable rigor and quiet intensity was already at work. Gerard Hooft, a Nobel laureate renowned for his foundational work in the quantum theory of fundamental forces, was a physicist's physicist, a man who trusted mathematics as his only guide. He was not a showman, not a purveyor of wild, speculative fantasies. His genius lay in his unflinching, logical pursuit of truth, following the threads of equations wherever they might lead, no matter how strange the destination. For Ain't Hooft, the random thermal nature of Hawking's radiation was an affront to quantum order. It felt messy, incomplete, an arbitrary erasure of cosmic memory that violated the deep-seated quantum principles he held sacred. He began to think not about the black hole as a whole, but about the individual particles that comprise it, about the delicate dance of cause and effect at the quantum level. Imagine, he reasoned, a single particle, an electron poised at the edge of the abyss. It carries with it a universe of information, its mass, its charge, its spin, its momentum. When it falls across the event horizon, does all of that simply vanish from our universe? Relativity said yes, it's gone forever. Hawking's equations said yes, its information is ultimately scrambled into meaningless heat and radiated away to nothing. But 't Hooft's quantum intuition screamed no. An effect must have a cause, and a cause must leave an effect. The particle cannot just disappear without a trace. He fixated on the one interaction that infalling matter would have with the outside world, its gravity. Even a single tiny particle possesses its own gravitational field, a minuscule but real distortion in the fabric of space-time around it. As it plunges towards the black hole, its gravitational influence doesn't just switch off. It must, Hooft calculated, leave a permanent mark, a subtle but undeniable deformation. But where would this mark be left? The particle itself is lost to the singularity deep inside the black hole's hidden core. The only interface between the interior and the exterior, the only place where a record could be kept, was the event horizon itself. This was 't Hooft's first revolutionary leap. He envisioned the event horizon not as a smooth, featureless veil, but as a dynamic surface capable of storing information. He realized that the gravitational field of the infalling particle would create a tiny localized bump or shift on the horizon's surface, a fleeting gravitational shockwave that permanently alters its geometry. Think of it like a name carved into wet cement. The particle is the stylus plunging through, but the inscription it leaves behind on the surface remains long after the stylus is gone. This subtle imprint, this gravitational memory, would then influence the Hawking radiation emitted from that exact spot. The radiation would no longer be random. It would be subtly encoded with the information of the very particle that created the deformation. The information wasn't lost, it was just transferred. It was a breathtaking idea, a piece of sheer mathematical audacity. Hooft was proposing that the three-dimensional information of a particle was being somehow translated or smeared or projected onto the two-dimensional surface of the event horizon. The implications were staggering, almost heretical. It suggested that the third dimension, the dimension of depth leading into the black hole, might be an illusion from the outside. That all the complexity, all the history, all the reality of what fell inside could be fully and completely described by a set of physical laws operating on its boundary. He didn't yet have a name for it, but he had uncovered the first crucial architectural sketch of a new cosmic blueprint, a hint that reality might be written in a language far stranger than we knew. The universe 't Hooft was beginning to see might be keeping its records in a very peculiar way indeed. Across the Atlantic in California, a very different kind of physicist was waging his own war against the paradox. Leonard Susskind, a pioneer of string theory, was everything. 't Hooft was not a brash, outspoken intellectual brawler, famous for his fierce debates and his intuitive visual style of thinking. If 't Hooft was the meticulous architect, Susskind was the passionate sculptor, moulding and wrestling with ideas until they took a shape that felt right. He called himself an 't Hooft certified crackpot for even taking the paradox seriously, for refusing to accept the comfortable consensus that Hawking was right. Susskind's path to the same revelation came not from the fine-grained analysis of particle gravity, but from a profound thought experiment rooted in the clash between quantum mechanics and an observer's point of view. He called it black hole complementarity. He asked you to imagine a spaceship perhaps carrying an elephant falling toward a black hole, and he asked you to consider two different perspectives. First, there is your perspective watching safely from a great distance. According to Einstein's theory of relativity, as the spaceship gets closer to the immense gravity of the black hole, time for the spaceship begins to slow down relative to you. Its light becomes stretched, redshifted. From your vantage point, you would see the spaceship slow and slow and slow approaching the event horizon, but never quite reaching it. It would appear to flatten against the horizon like a bug pressed against a window pane, its image getting dimmer and more distorted until it effectively freezes and fades away over an eternity. From your point of view, the elephant and its information never cross the boundary. They are pancaked onto the two-dimensional surface, their information smeared across it, and then slowly radiated back out as Hawking radiation. For you, the distant observer information is never lost. It's simply held at the border and returned. But now consider the second perspective, that of an astronaut inside the falling spaceship. For them, there is no drama at the event horizon. According to Einstein's equivalence principle, free fall is indistinguishable from floating in empty space. They would feel no jolt, see no wall of fire, perceive no boundary at all. They would sail smoothly across the event horizon, unaware that their point of no return had been passed only to be eventually torn apart by the tidal forces and crushed in the singularity. From their perspective, their information passes into the black hole's interior. Here was the paradox in its starkest form. You, the outside observer, see the elephant's information plastered on the surface. The astronaut sees the elephant's information fall inside. Which one is real? Does a quantum copy of the elephant get created, one inside and one outside? Quantum mechanics has another ironclad rule: you cannot clone information. It would be a violation of a principle called quantum no cloning. So, the elephant's information must be in one place and one place only. This is where Susskind had his brilliant, almost Zen-like epiphany. He proposed that both perspectives are correct, and they are not contradictory because they are complementary. No single observer can ever see both outcomes. You, the outsider, can never see inside the event horizon. The astronaut, the insider, can never send a message back out to you after they've crossed. Since no one can ever perform an experiment that proves the information is in two places at once, there is no operational paradox. It is a single reality described in two completely different but equally valid ways. The crucial insight, however, was what this meant for the location of information. For any observer on the outside, which includes all of us in the universe, the story is unambiguous. Everything that has ever fallen into a black hole, every star, every planet, every single atom has its information content completely and utterly imprinted upon the two-dimensional event horizon. It's not just stored there. In a very real sense, from our perspective, it is times there. Susskind, coming from the world of string theory, where fundamental objects are not points but vibrating strings, found this idea natural. Strings themselves were one-dimensional objects that vibrated, and as they approached the horizon, he could visualize them spreading out their vibrations, encoding their information across the surface membrane of the black hole. He had arrived at the exact same mind-bending conclusion as 'Hoofd. From opposite ends of the physics world, through different lines of reasoning and different styles of thought, these two intellectual warriors had converged on a single radical solution. The secrets of a black hole were not locked away in some unknowable three-dimensional vault. They were written in plain sight on its surface. It was in the fusion of these two streams of thought that the true power of the idea was unleashed. Susskind, with his flair for evocative language, gave it the name that would ignite the field: the holographic principle. The name was a direct analogy to the holograms you might see in a museum or on a credit card. A hologram is a remarkable thing. It is a flat, two-dimensional piece of film. Yet when you shine a laser through it, it projects a full three-dimensional image, complete with depth and parallax, an image that appears to have volume and substance. All the information required to describe the complex 3D object is somehow miraculously encoded point for point onto the 2D surface of the film. This, they proposed, is exactly what a black hole is doing. The event horizon is the holographic plate. The three-dimensional volume inside the black hole, with all the matter and energy it has consumed, is the projected image. It was a paradigm shift of seismic proportions. We have always been taught to think of information as something that occupies volume. The information in your brain is stored in a 3D network of neurons. The information in a book is stored on many pages, which together have volume. But for a black hole, the ultimate repository of information, this intuition fails completely. The maximum amount of information that can be contained within a region of space is not proportional to its volume as one would expect, but to its surface area. It's as if you tried to fill a warehouse with filing cabinets, only to discover that you could only store as much information as could be painted on the building's outer walls. It makes no logical sense in our everyday world, yet in the extreme physics of a black hole it appeared to be true. The surface of the event horizon could be imagined as being tiled with the smallest possible units of area known as Planck areas. impossibly tiny squares 100 million trillion times smaller than a proton. Each of these minuscule pixels on the cosmic screen can hold exactly one fundamental bit of information, one yes or no. And the total number of these pixels on the black hole's surface is precisely enough to account for all the information that ever fell in. The information paradox, the crisis that had haunted physics for decades, was suddenly resolved, albeit in the strangest way imaginable. Information is not destroyed when it falls into a black hole. It is captured and meticulously encoded on the event horizon, which acts as a vast celestial ledger. And what of Hawking radiation? It is no longer a random memory-wiping thermal hiss. Instead, it is the slow, painstaking process of the hologram being read. As the black hole evaporates, each quantum of radiation that escapes carries with it a tiny scrambled piece of the information from the surface. If you could capture every single particle of Hawking radiation over the eons, it takes a black hole to disappear, and if you possessed a quantum computer of unimaginable power, you could, in principle, reconstruct everything that ever fell. You could retrieve the information of the elephant, the starship, the collapsed star. The universe in this new picture is the ultimate cosmic librarian. It never destroys its books, it merely translates them into a different, more compact language and stores them on a different shelf. The law of information conservation is upheld, the quantum scripture remains sacred. The scientific community was stunned into a state of profound cognitive dissonance. On the one hand, the holographic solution was beautiful, elegant, and it appeared to solve the deepest paradox of modern physics. On the other hand, it seemed utterly insane. It suggested that our intuitive understanding of space of locality, the idea that things happen at a specific point in 3D space, was fundamentally wrong. If all the information about a 3D volume could be encoded on a 2D surface, then which was more real? The surface or the volume, the description or the thing being described? This wasn't just a new theory about black holes anymore. This was a confrontation with the very nature of reality itself. The idea that began as a desperate attempt to patch a hole in quantum theory had torn open a much larger, more tantalizing abyss of a question. If this strange holographic rule applies to the most information-dense objects in the cosmos, if gravity forces information to live on a surface in this extreme case, then might this not be a clue to a universal principle? Could it be that the holographic nature of black holes is not an exception, but a magnified example of a deeper truth? A truth that applies not just to these exotic cosmic prisons, but to everything, to this room, to this planet, to you, and to the entire universe we inhabit. The stage was now set for the most dramatic intellectual leap of all, to take the principle out of the black hole and apply it to the whole of existence. And so a paradox born in the crushing heart of a dead star had rippled outwards, shaking the very foundations of what we thought we knew about reality itself. Information, it seemed, was not destroyed, but was instead meticulously encoded, painted onto the stretched fabric of the event horizon, a cosmic archive written in a language of quantum mechanics that we were only just beginning to decipher. The black hole, once imagined as the universe's ultimate dead end, had revealed itself to be a page of a book we never knew existed. For physicists like Leonard Susskind and Gerard Hooft, this was more than a victory. It was a revelation that pointed towards something far deeper, far more unsettling. If the entire complex three-dimensional story of a collapsed star could be perfectly stored on its two-dimensional boundary, then a tantalizing, almost terrifying question began to whisper in the corridors of theoretical physics. What if this wasn't just a strange property of black holes? What if this was a fundamental rule of the cosmos? Could it be that we had stumbled upon a universal principle, a law of nature as profound as gravity or the speed of light? Audacious thought began to take shape. Perhaps we and everything we have ever known are merely the intricate projection of information stored on some distant, unseen boundary at the edge of the universe. It was a leap of logic so immense it bordered on madness. To propose that the solid, tangible reality you perceive around you, the chair you are sitting on, the air you are breathing, the starlight that traveled for millions of years to reach your eyes, is fundamentally an illusion, a grand hologram. was to challenge the bedrock of human experience. For years, this idea remained a powerful yet ghostly speculation. It was a beautiful and haunting melody with no orchestra to play it, a concept lacking the rigorous mathematical score needed to transform it from philosophical musing into hard science. The holographic principle was an answer without a provable equation, a destination without a map. The problem was one of translation. How could you possibly create a mathematical dictionary that could flawlessly convert the complex dynamic language of a three-dimensional universe filled with gravity, curved space-time, and tangible objects into the starkly different language of a two-dimensional surface governed only by the peculiar rules of quantum particles? It seemed like trying to describe a symphony using only colors or capturing the experience of a human life in a single line of code. The two worlds, one of gravity and geometry, the other of quantum fields and probabilities, appeared utterly incompatible, separated by a seemingly unbridgeable chasm. Without a concrete model, a working example, the holographic principle was destined to remain a footnote in the history of brilliant but unproven ideas. The world of physics needed a Rosetta Stone, and then in 1997 it arrived. It came not from a grand experimental discovery, but from the mind of a young Argentine-American theoretical physicist named Juan Maldacena. Working quietly at Harvard University, he published a paper that would almost overnight ignite a revolution that is still burning brightly today. It wasn't a theory of our specific universe, not yet. Instead, it was something more profound, a perfect, mathematically pristine example of the holographic principle in action. He had discovered a magical duality, a hidden bridge connecting two vastly different theoretical universes, proving they were against all intuition exactly the same thing. This discovery, known formally as the anti-de Sitter, conformal field theory correspondence, or ADES, CFT for short, became the bedrock upon which all modern holographic thinking is built. It was the score for the haunting melody, the map to the impossible destination. It was the moment the ghost in the machine finally showed its face. To understand Maldacena's breakthrough, you first have to let go of the universe, you know. You must imagine a cosmos with a completely different geometry, a peculiar theoretical space called anti-de Sitter space. Unlike our universe, which appears to be expanding outwards, anti-de Sitter space is a universe with a boundary, a definitive edge. It's a strange, warped reality. Picture it not as an expanding sphere, but as an infinite cosmic cavern, or perhaps a can of soup of infinite height and depth. In this universe, space is negatively curved like a saddle. A beam of light sent out from the center would travel to the boundary, reflect off it, and return to the center in a finite amount of time, no matter how far that boundary seemed to be. Gravity in this universe behaves strangely too. It constantly pulls things towards the center, preventing anything from ever actually reaching the outer edge. This ADES space is the bulk of Maldacena's model, a complete self-contained universe with its own dimensions and its own powerful laws of gravity governed by the complex equations of string theory. It is a universe where space-time can bend and ripple, where black holes can form and evaporate, a rich dynamic gravitational world existing in, for example, 5 dimensions. It is, for all intents and purposes, the 3D object in our holographic analogy, though it may have many more dimensions than that. Now imagine the surface of this infinite can, its 2-dimensional boundary. This boundary is where the hologram lives. On this lower dimensional surface exists a completely different kind of reality. It is a world described by something called a conformal field theory, or CFT. This is a universe without gravity. There is no space-time to be curved, no apples falling from trees, no planets orbiting stars. Instead, it is a flat, shimmering tapestry woven from the bizarre and counterintuitive rules of quantum mechanics. It is populated by a zoo of subatomic particles interacting with each other, entangling and behaving according to the precise laws of quantum fields. Think of it as a chaotic, flickering film of quantum information, a frantic dance of particles on a flat, rigid stage. There is no up or down in the gravitational sense, only the ceaseless hum of quantum activity playing out across a surface. This boundary world, this CFT, seems to have absolutely nothing in common with the vast, curved gravitational universe of anti-de Sitter space that it encloses. One is a world of geometry and gravity. The other is a world of quantum chaos. They speak completely different languages. They obey completely different laws. They appear to be two entirely separate, unrelated universes. This is where Juan Maldacena unveiled his stroke of pure genius. He demonstrated with unimpeachable mathematical rigor that these two descriptions were not just related, they were perfectly equivalent. They were a duality. A dictionary that could translate every single statement, every event, every object in the gravitational ADS universe into a corresponding statement about the quantum particles on the lower dimensional CFT boundary, and the translation was perfect in both directions. Anything that happened inside the five-dimensional gravitational bulk space had a direct calculable counterpart in the four-dimensional non-gravitational quantum boundary theory. A black hole forming in the center of the ADS universe. This corresponds to a specific configuration of hot interacting particles swirling on the boundary like a thermal fluid. An object falling towards that black hole, this is perfectly mirrored by the way information about that object spreads out and scrambles among the quantum particles on the surface. The evaporation of that black hole via Hawking radiation, this is equivalent to the system of boundary particles slowly returning to a state of thermal equilibrium. It was staggering. Maldacena had found the Rosetta Stone. The implications of this AD-S CFT correspondence were seismic. It meant that the two universes, the gravitational world inside and the quantum world on its surface, were not two separate realities. They were two different mathematical descriptions of the time's exact same underlying phenomenon asterisk. One is the hologram, the other is the projection. Which one is more real? The question itself becomes meaningless. They are both equally fundamental, equally true. It's like having a musical score and the symphony it produces. The score is a two-dimensional set of symbols on paper. The symphony is a rich, three-dimensional experience of sound filling a concert hall. They are utterly different descriptions, yet they contain precisely the same information. One is a perfect mapping of the other. Maldacena had shown that at least in this specific theoretical model, a universe with gravity is a symphony, and its hologram is the musical score written on the boundary of space-time. For the first time, the holographic principle was no longer a philosophical flight of fancy. It was now a powerful computational tool, a concrete mathematical framework that physicists could actually use. It provided a stunning new paradigm for thinking about reality. Most importantly, it offered a way to tackle some of the deepest, most intractable problems in all of physics. The monster at the heart of modern science has always been the profound incompatibility between our two greatest theories. Einstein's general relativity, which describes the large-scale world of gravity and space-time, and quantum mechanics, which describes the small-scale world of particles and forces. These two theories work perfectly in their own domains, but when you try to merge them to describe situations where extreme gravity and quantum effects are both important, like the singularity inside a black hole or the first moment of the Big Bang, the mathematics breaks down into nonsense. String theory was the leading attempt to unify them, but its equations were notoriously, perhaps impossibly difficult to solve. The AD-CFT correspondence offered a spectacular backdoor entrance to this problem. It created a gravity quantum dictionary. Suddenly, a fearsomely difficult problem involving quantum gravity in the ADS bulk could be translated into a much simpler, more manageable problem about quantum particles on the boundary where gravity doesn't exist, and vice versa. Questions about the strange behavior of certain exotic materials governed by complex quantum interactions could be translated into simpler questions about the geometry of black holes in a higher dimensional universe. Physicists began using this holographic dictionary to study everything from the quark-gluon plasma created in particle accelerators to the properties of high-temperature superconductors. It was as if we had spent centuries trying to climb an unscalable cliff face only to be handed a map showing a hidden tunnel that led straight to the summit. The correspondence provided a mathematical playground, a theoretical laboratory where the confounding relationship between gravity and quantum mechanics could be explored in a perfectly controlled, self-consistent way. It gave substance to the shadow. It gave a voice to the ghost. It confirmed that at least in one corner of the theoretical cosmos, the universe could indeed be a hologram. The discovery sent shockwaves through the physics community, transforming Juan Maldacena into one of the most cited scientists of his generation. The holographic principle was no longer just a curious observation about the entropy of black holes. It had been elevated to a central organizing principle, a new way of thinking about the very nature of space-time and information. It suggested that the geometry of space-time itself might not be fundamental. Perhaps space-time is an emergent property, a geometric illusion constructed from the more basic reality of entangled quantum bits living on a distant boundary. In this view, the universe isn't a stage upon which the quantum drama unfolds. The quantum drama, the entanglement of particles on the surface times, builds the stage asterisk. The connectivity of space, the very idea of here and there, might be nothing more than a manifestation of quantum connections. Two entangled particles on the boundary, no matter how far apart, could be creating a connection through the bulk, a wormhole, a shortcut through space-time. The fabric of the cosmos, it seemed, might be woven from quantum threads, but for all its power and elegance, a colossal question mark hung over Maldacena's discovery. The AD-CFT correspondence was a perfect proof of concept, a working model, but it was a model of a toy universe. The anti-de Sitter space at its heart is a universe with a distinct mathematical structure, a negative curvature that pulls everything inward. Our universe is not like that. When we look out at the cosmos, we see something startlingly different. We see galaxies rushing away from each other at an ever-increasing speed, propelled by a mysterious force we have labeled dark energy. Our universe appears to have a positive curvature, not a negative one. It is a de Sitter space, not an anti-de Sitter space. It is expanding, accelerating, and it has no obvious boundary like the one in Maldacena's idealized model. And so the ultimate question remained unanswered, hanging in the cosmic dark. The Rosetta Stone had been found, but it was written for a different language, a different civilization. It proved that holography times could times be a feature of a universe, but it didn't prove it was a feature of times our times universe. The central challenge for physicists now became clear. Could they adapt this revolutionary idea? Could they find a way to formulate a holographic principle for a universe like ours, an expanding, accelerating cosmos racing towards an unknown future? The search was on for a new page in the cosmic dictionary, one that could translate the story of our own reality and reveal whether we too are merely shadows projected from the edge of time. So a perfect correspondence, a flawless mathematical dictionary translating one world into another. A universe of strings and quantum gravity mirrored with astonishing precision by a simpler, flatter reality of ordinary particles and fields. It was a theoretical triumph, a moment of profound revelation that sent shockwaves through the world of physics. We had found a working model, a toy universe in a bottle where the holographic principle wasn't just a conjecture, it was a mathematical fact. But this triumph, as magnificent as it was, came with a deeply unsettling caveat. The map we had so brilliantly deciphered, this perfect anti-de Sitter space, was for a cosmos that is not our own. We had found the key to a lock on a door that doesn't exist in our home. Our universe is a profoundly different beast. It isn't nestled inside a reflective static boundary. It doesn't curve inward on itself into a neat, predictable container. Our cosmos, as we have painstakingly observed, is doing the exact opposite. It is expanding, and that expansion is accelerating, driven by a mysterious dark energy that pushes everything apart. We live in what physicists call a de Sitter universe, a place with a positive cosmological constant, and unlike the tidy confines of anti-de Sitter space, our cosmic boundary is not a static wall you can project a hologram onto. It is a horizon, an ever-receding veil called the cosmological horizon, a point of no return that races away from us at the speed of light. The screen for our hologram, if it exists, is not a fixed backdrop. It is a shimmering, dynamic, and seemingly inaccessible mirage at the edge of observable reality. This is the chasm that separates a beautiful piece of mathematics from the tangible universe you inhabit. And it is down this path into this chasm of uncertainty that we must now travel. For if we are to take the holographic principle seriously, if we are to even consider that our three-dimensional existence is an elaborate projection, then we must confront what that means for everything we hold fundamental. We must be willing to let go of our deepest intuitions about the nature of space, the flow of time, and the very force that holds our world together. We must face the possibility that the solid ground beneath our feet is a phantom and the force of gravity is a ghost. Let's begin with the fabric of reality itself. In our everyday experience, space is the stage. It is the absolute pre-existing arena in which the drama of the universe unfolds. It is the three-dimensional void you move through the where for every event. But in a holographic cosmos, this entire concept is turned on its head. Space is no longer fundamental. It is an emergent property, a magnificent illusion constructed from something far more basic information. Imagine a vast two-dimensional surface at the boundary of the cosmos, a celestial canvas tiled with an unimaginable number of quantum bits or qubits. These are the fundamental units of reality, the source code of existence. Each qubit on this surface isn't just a simple 0 or 1. It exists in a quantum superposition, a haze of possibilities. And crucially, these qubits are not independent. They are connected through the strange and wonderful phenomenon of quantum entanglement. This is the spooky action at a distance that so troubled Einstein, where the state of one qubit is inextricably linked to the state of another, no matter how far apart they are on the surface. It is from this intricate web of entanglement that the illusion of three-dimensional space is born. The geometry of our world, the very notion of distance, is nothing more than a manifestation of the entanglement patterns on that distant screen. Think of it this way. Two qubits on the boundary that are highly entangled with each other manifest in the three-dimensional projection as 2 points that are very close together in space. Two qubits that are not entangled at all appear as points that are vast distances apart. The more threads of entanglement connecting different regions of the boundary, the more warped and curved the corresponding region of space-time becomes in the bulk. What we perceive as the empty vacuum of space is in this picture a seething, intricate network of quantum connections. The fabric of the cosmos is literally woven from threads of pure information. This means that if you could somehow snip the threads of entanglement between two sets of qubits on the boundary, the space between their corresponding points in our universe wouldn't just stretch, it would cease to exist. The connection would be broken and the space itself would tear apart. This reconceptualization is so profound it's difficult to fully grasp. When you look up at the night sky at a distant galaxy millions of light years away, you are not seeing an object across an immense void. You are seeing the holographic projection of a set of qubits on the cosmic boundary, whose entanglement with the qubits that project to you is incredibly weak. The vastness of space is a measure of quantum disentanglement. The very architecture of our universe, its grand cosmic web of galaxies and voids, is a geometric map of the quantum correlations on a two-dimensional surface we can never visit. We are living inside the image, utterly convinced of its solidity, while the machinery of reality whirs away on a distant, lower-dimensional screen. And what of time? If space is an illusion, time fares no better. The steady forward march of time from past to present to future feels like the most fundamental aspect of our existence. But in the holographic universe, time too is emergent. On the two-dimensional boundary, there is no master clock, no universal now. There are only the timeless mathematical relationships between qubits, the frantic quantum computations unfolding according to the laws of quantum mechanics. The flow of time that we experience in our three-dimensional world is in essence a measure of the increasing complexity of these computations. It is the shadow of the universe's ongoing information processing. As the quantum state on the boundary evolves, becoming ever more complex and entangled, our perception within the hologram is of a universe progressing through time. A cosmic event like the explosion of a supernova is not something that happens at times, a moment in time. It is a reflection of a dramatic and rapid reorganization of information on the boundary, a cascade of quantum calculations that we, as projected beings, interpret as a sequence of events unfolding over days, weeks, and months. This demotes time from its role as the river on which reality floats to something more like the ticking of the cosmic processor. It suggests that at the most fundamental level of reality, the distinction between past, present, and future might simply melt away, leaving only the timeless logic of the quantum code. This radical reimagining of space and time forces us to confront the biggest player on the cosmic stage, gravity. For centuries, we have seen gravity as an elemental force of nature. First, it was Newton's mysterious pull, an invisible rope connecting every mass in the universe. Then it was Einstein's masterpiece, the elegant curvature of space-time itself, a geometric stage that tells matter how to move, while matter tells the stage how to curve. In Einstein's view, gravity is woven into the very fabric of the cosmos. It is as fundamental as space and time because, in a way, it times space and time. But the holographic principle delivers the most shocking verdict of all. If space and time are not fundamental, then gravity cannot be either. Instead, gravity must be an emergent phenomenon, an illusion born of other, deeper processes. It's less a fundamental force and more of a thermodynamic effect, a cosmic-scale consequence of the statistics of information. This idea connects back to the very origins of the holographic principle, to Jacob Bekenstein and Stephen Hawking's work on black holes. They discovered that the laws of black hole mechanics looked suspiciously like the laws of thermodynamics. A black hole's surface area behaves like entropy, a measure of hidden information. This wasn't a coincidence. It was the first profound clue that gravity is somehow related to the flow and storage of information. In the holographic picture, this idea becomes concrete. The force we call gravity is not a pull. It is not the warping of a geometric stage. It is, in essence, the universe's relentless tendency to maximize its own entropy. The quantum bits on the boundary surface are constantly interacting, evolving towards states of higher probability and greater disorder. Just like a drop of ink spreading out in a glass of water, this statistical drift towards chaos on the boundary screen manifests itself in our three-dimensional world as the force of gravity. A planet orbiting a star isn't being pulled by a rope or following a curve in a cosmic trampoline. The configuration of matter and energy that constitutes the planet and the star is simply the most statistically likely projection of the underlying quantum information on the boundary. The orbit is the path of least resistance for the information itself. This makes gravity an entropic force. It's what physicists call a bookkeeping effect. It's no more fundamental than the concept of temperature or pressure in a gas. A single molecule in a box does not have a temperature. Temperature is an emergent statistical property of countless molecules bumping into each other. In the same way, a single qubit on the boundary doesn't generate gravity. Gravity is the collective statistical behavior of an astronomical number of entangled qubits. It is the thermodynamic sigh of the cosmos, the large-scale consequence of the microscopic dance of information. This is perhaps the most audacious and challenging claim of the entire holographic framework, that the force that binds galaxies, ignites stars, and holds you to the Earth is a phantom, a shadow cast into our dimensions by the quantum chaos, playing out on a distant surface. This connection between geometry and information is encapsulated in one of the most provocative and mind-bending ideas to come out of modern physics, a simple-looking equation with profound implications: ER equals EPR. This is a conjecture that connects two pillars of 20th century physics. EPR stands for the Einstein-Podolsky-Rosen paradox, which first highlighted the bizarre nature of quantum entanglement. ER stands for Einstein-Rosen bridges, better known as wormholes, tunnels through the fabric of spacetime. The conjecture proposes that these two seemingly unrelated concepts are in fact one and the same. Every instance of quantum entanglement between two particles is in the geometric language of the bulk, a microscopic wormhole connecting them. This is the mechanism. This is how information builds space. The quantum stitches that hold our universe together are these tiny, non-traversable wormholes. The entire intricate geometry of space-time, with all its curves and warps that we interpret as gravity, is a vast switchboard of these entanglement wormhole connections. When you have two black holes that are entangled with each other, they are connected by a wormhole. As they drift apart in our three-dimensional space, the wormhole connecting them grows longer. This idea provides a stunningly tangible model for how the purely informational concept of entanglement can give rise to the purely geometric concept of space-time. The phantom force of gravity is the large-scale tension in this cosmic web of quantum threads. Our universe isn't just a hologram. It is a hologram whose very pixels are stitched together with wormholes. But for all its explanatory power and mathematical elegance, this entire structure faces one monumental, perhaps insurmountable obstacle: the de Sitter problem. How do you apply these ideas to times our times universe? The success of the holographic principle in anti-de Sitter space relied entirely on the existence of a fixed, timeless boundary where the two-dimensional quantum field theory could live. It was the ultimate stable projection screen. But our universe has no such thing. Our boundary, the cosmological horizon, is a dynamic and observer-dependent surface. The location of your horizon depends on your motion. Two people moving relative to each other in our accelerating universe will have different cosmic horizons. So, which one is the true holographic screen? Where is the real two-dimensional theory located? Furthermore, the horizon of our universe is a thermal surface. It radiates energy much like a black hole horizon, giving it a temperature. This implies it has entropy, a finite amount of information it can contain. This is a good sign, a hint that a holographic description might be possible. But the screen is also expanding. As the universe expands, the surface area of the cosmological horizon grows, meaning the total number of bits required to describe the universe is increasing. Where does this new information come from? How can a quantum theory with a fixed number of degrees of freedom describe a cosmos whose information content seems to be perpetually growing? And perhaps most perplexing of all is the problem of time. In the anti-de Sitter model, time flows the same way in the bulk and on the boundary. They share a universal clock. But in our de Sitter universe, time is a slippery concept. The accelerating expansion warps time itself. Clocks at the edge of the observable universe would appear to us to be frozen. How do you map the dynamic evolving time of our three-dimensional experience onto a quantum system living on a boundary where time behaves so strangely? These are not minor technicalities. They are deep foundational paradoxes that strike at the heart of the holographic enterprise. Physicists have been battling these questions for decades, proposing ingenious but speculative models like DS, CFT correspondence, or the idea of a hologram within a hologram, but a consensus remains elusive. It's like trying to project a film onto a screen made of billowing smoke. The picture is unstable, ill-defined, and constantly shifting. This is the downward path of scientific inquiry. It is the descent from the peak of a beautiful, solvable problem into the dark and tangled valley of reality. And as we descend, the implications become less mathematical and more personal, forcing a confrontation with our own perception of existence. If the holographic principle holds true for our universe, what does that say about us? You are a being of staggering complexity, a collection of roughly 7 octillion atoms organized into cells, tissues, and a conscious mind. You feel the solidity of the world, the warmth of the sun, the passage of time. You make choices, you feel emotions, you experience the universe as a three-dimensional agent. But the hologram suggests that all of this, your body, your brain, your thoughts, is ultimately a projection. Your entire being is a complex pattern of information encoded on a distant two-dimensional surface. The electrical signals firing in your neurons, which you experience as a thought or a memory, are the holographic reflection of quantum processes happening somewhere else entirely. This raises philosophical questions of a staggering magnitude. If our actions are encoded on a boundary governed by deterministic quantum mechanics, what does that mean for the concept of free will? Are we simply watching a pre-recorded movie, our choices an illusion created by the unfolding of the cosmic source code? Does our consciousness reside herein for this three-dimensional projection, or is it somehow tied to the informational process on the boundary? Are we characters in a story profoundly convinced of our own autonomy, while the true authors reside in a different dimension entirely? This is not just a scientific theory, it is a challenge to our identity. It suggests that the distinction between the observer and the observed, between mind and matter, might be yet another emergent illusion. We might be nothing more than the universe's way of perceiving its own holographic information. The experience of being you is the projection of a certain subset of bits on the cosmic screen, a temporary self-aware pattern in the grand computation. The vertigo of this realization is immense. It asks us to accept that the most real things in our lives, the physical world, our own bodies, the flow of time, are derivative. They are high-level descriptions of a more fundamental and profoundly alien reality. We are like characters in a hyper-realistic video game, unaware that our entire world is just information being rendered on a two-dimensional screen. We are so immersed in the game that we have forgotten we are part of it. The laws of physics we have discovered from Newton to Einstein would be the rules of the game's engine, fantastically consistent and predictive, but ultimately not the fundamental code. The downward path has led us here to the edge of a philosophical abyss. We stand confronted by the profound challenges of the De Sitter universe and the deeply unsettling implications for our own existence. The clean, elegant solution found in a toy universe has given way to a messy, paradoxical, and existentially troubling reality. The theory, for all its power, has taken us into a labyrinth of its own making. And within this labyrinth, we are forced to ask the ultimate question: how could we ever know for sure? How could we, the projections, ever hope to prove the existence of the projector? Mathematics and theory alone, it seems, cannot provide the final answer. To escape this maze, we must turn from the abstract world of equations and look for a crack in the illusion, a glitch in the cosmic code. We must search for a tangible physical clue, the very first pixel of the universal hologram. The mathematical elegance is almost seductive. In the pristine world of theory, where dimensions can be folded and space-time is a malleable fabric, the holographic principle offers a breathtaking vision of unity, a glimpse of the universe's deepest operating system. But physics is not a work of pure mathematics. It is an empirical science, a grand conversation with reality that demands evidence. The most beautiful idea is nothing more than a beautiful dream if it cannot be tested, if it leaves no discernible trace on the cosmos we can actually observe. And so we are driven from the serene comfort of the whiteboard into the chaotic, noisy, magnificent laboratory of the universe itself. The quest begins not with equations, but with a question that is almost childlike in its simplicity. If we are living inside a hologram, can we see the pixels? This is the profound and audacious challenge that confronts a new generation of experimental physicists. They are hunters searching for the fundamental graininess of reality, the ultimate resolution of the cosmic screen. If the three-dimensional world you experience is truly a projection, then like any projected image, it cannot have infinite detail. Zoom in far enough past the atoms, past the quarks, past the very concept of location as you know it, and you should, in principle, find the edge of information. You would find the elemental bit of reality, the Planck length, where the smooth continuity of space and time breaks down into a quantum fuzz, a jittery, uncertain froth. This is the holographic signature we are looking for. But how do you possibly measure a pixel whose size is to a single atom, as that atom is to the entire visible universe? You cannot build a microscope powerful enough. Instead, you must build an instrument that can listen. Listen for the noise of space-time itself. Imagine a perfect digital photograph. From a distance, it is a smooth, continuous image. But as you magnify it again and again, you begin to see the grid, the individual pixels that constitute the whole. And at this boundary of information, there is an inherent uncertainty, a fundamental flicker. Physicists theorize that if our universe is holographic, then space-time itself should exhibit a similar effect. A constant, irreducible holographic noise, a microscopic tremor as the universe jitters between its possible quantum states. It would be the quietest sound in the cosmos, a hum baked into the very structure of existence, a shiver in the void. To hear this shiver, a team at the Fermi National Accelerator Laboratory embarked on one of the most daring experiments in the history of physics. They built a machine called the holometer. It was an instrument of almost absurd sensitivity. The holometer consisted of two identical L-shaped devices called interferometers placed side by side. At the heart of each machine, a powerful laser beam was split in two, sent down perpendicular arms, 400 meters long, and then reflected back by perfectly polished mirrors. When the two beams recombined, they created an interference pattern, a delicate dance of light and dark fringes. The position of these fringes is exquisitely sensitive to the tiniest vibrations, to any change in the distance the laser beams travel. This is technology we have mastered for detecting gravitational waves, the great cosmic tsunamis of space-time. But the hologometer wasn't looking for a singular violent event like the collision of two black holes. It was listening for something infinitely more subtle. It was trying to detect a background hum, a persistent correlated jitter in both machines at once. The theory was this: if one interferometer detected a random shiver, it could be anything, a passing truck, a distant earthquake, thermal expansion in the machinery. But if both independent machines, isolated from each other, quivered in perfect synchrony with no identifiable earthly cause, it would be a monumental discovery. It would be evidence that the vibration was not in the machine, but in the very space the machine occupied. It would be the telltale sign of holographic noise, the jitter of the cosmic pixels. For years, the holometer listened with unprecedented focus, shielded from seismic noise, running in a vacuum, calibrated to a precision that strains the imagination. It was designed to measure a wobble in space-time 1,000 times smaller than the nucleus of an atom. The global physics community watched and waited. The data streamed in a torrent of information from the quietest place on Earth, a place designed to hear the whispers of reality. The analysis was painstaking, filtering out every conceivable source of terrestrial and instrumental noise, and the result, silence. The holometer heard nothing. No correlated jitter, no holographic hum, no evidence that space-time was pixelated, at least not at the scale it was designed to detect. For some, this was a deep disappointment, the closing of a door on a dramatic and direct path to proving the holographic principle. But in science, a null result is not a failure. It is a crucial piece of information. The holometer's silence didn't kill the holographic principle. It refined it. It placed a strict new limit on the nature of reality. It told us that if the universe is a hologram, its pixels are even smaller, its resolution even higher, its structure even more perfectly smooth than some theories had predicted. The search for the cosmic pixel was not over. It had simply been forced to move to a new, even grander arena. If the graininess of space-time is too subtle to detect on a tabletop, perhaps its signature is not a sound but an image written across the entire sky in the oldest light in the universe. We turn our gaze from the laboratory to the cosmos, to the faint, pervasive afterglow of the Big Bang, the cosmic microwave background. This is the universe's baby picture, a snapshot of the cosmos, when it was just 3,800,000 years old, a hot, dense, glowing fog that has been stretched and cooled by 13.8 billion years of cosmic expansion. Imprinted on this ancient light are tiny, almost imperceptible variations in temperature, the seeds of all future structure. These minute fluctuations, these hot and cold spots, are the ancestors of every galaxy, every star, and ultimately you. Our standard model of cosmology, the reigning theory of cosmic origins, predicts the statistical distribution of these spots with stunning accuracy. It describes a universe born in a quantum fluctuation, inflated to astronomical size in a fraction of a second, and evolving according to the laws of general relativity. This model works beautifully. But it is based on the assumption that the universe was born as a fully fledged three-dimensional space. What if it wasn't? What if in its very first moments the universe was a two-dimensional field of information from which our third dimension of space had to emerge to unfurl like a cosmic pop-up book? This is the radical alternative, suggested by the holographic principle. And if this were true, this bizarre holographic birth might have left a specific telltale fingerprint on that first light. A projection, after all, is not the same as the real thing. It can have distortions, artifacts, and a different kind of texture. A team of theoretical physicists began to wonder if the statistical patterns in the cosmic microwave background contained such an artifact. They built a theoretical model of a holographic Big Bang, calculating what the cosmic afterglow would look like if it were a projection from a lower dimensional boundary. Their equations produced a specific complex set of predictions, a unique signature that could be compared to the real data gathered by our most powerful space telescopes, like the European Space Agency's Planck satellite. The hunt was on. Cosmologists began meticulously scanning the Planck data, a celestial treasure map of unparalleled detail. They were looking for subtle correlations in the temperature patterns for statistical anomalies that the standard 3D model of inflation could not easily explain, but which the 2D holographic model could, and astonishingly they found hints. The data, particularly on the largest angular scales across the sky, seemed to fit the holographic model slightly better than the standard inflationary model. The whispers grew louder. Could this be it? Could the evidence for our holographic reality be hiding in plain sight, painted across the entire heavens since the dawn of time? The possibility is tantalizing, a breakthrough that would redefine our place in the cosmos. But we must be ruthlessly cautious. The signal is faint, buried in cosmic uncertainty. The statistical preference is minor and could well be a fluke, a ghost in the data that will vanish with more precise measurements. The scientific jury is still very much out. The debate rages at conferences and in academic papers, a testament to the vibrant, self-critical nature of science. We stand on a knife's edge of understanding, peering into the murky data from the beginning of time, trying to discern whether we are looking at the genuine birth of a 3D universe, or merely the shadow of a 2D one. While the experimentalists search for these smoking guns for a definitive observational proof, the holographic principle is already waging a quiet revolution in the world of theoretical physics. It has become more than just a fascinating conjecture. It has become an indispensable tool, a guiding light in the darkest and most intractable wilderness of science, the quest for a theory of quantum gravity. For decades, this has been the holy grail of physics, a single, unified framework that can describe the universe at all scales, from the graceful waltz of galaxies governed by Einstein's relativity to the frenetic probabilistic dance of subatomic particles governed by quantum mechanics. The two leading contenders for this ultimate theory are string theory and loop quantum gravity, and the holographic principle resonates profoundly with both. In string theory, where fundamental particles are imagined as tiny vibrating strings of energy in higher dimensions, the holographic principle, especially through the AD-CFT correspondence, arrived like a Rosetta Stone. It provided a concrete, calculable dictionary to translate seemingly impossible problems about gravity in one space into more manageable problems about quantum particles on a lower dimensional boundary. Suddenly, physicists had a mathematical playground where they could safely explore the treacherous terrain of quantum gravity. They could probe the paradox of black hole information, simulate the physics of quark-gluon plasma, and test new ideas about the fundamental nature of space-time itself. The holographic principle gave string theory a powerful new toolkit, transforming it from a purely abstract mathematical framework into something that could make testable quantitative predictions. It acts as a check, a form of quality control. Any viable version of string theory, it is now widely believed, must incorporate holography at its very core. If it doesn't, it's likely a dead end. Loop quantum gravity, the main rival to string theory, approaches the problem from a completely different direction. Instead of starting with particles, it starts with space-time itself, imagining it not as a smooth sheet, but as a woven fabric built from discrete, indivisible quantum loops. In this picture, space is literally composed of atoms of geometry, and remarkably, this theory has holography built into its DNA. When loop quantum theorists calculate the entropy of a black hole, they find it is not proportional to the volume enclosed by the event horizon, but to its surface area. The area of the horizon is literally defined by the number of quantum threads of spacetime that puncture it. Information is not stored inside the volume, but is encoded on the surface exactly as the holographic principle demands. So here we have two radically different approaches to quantum gravity, born from different philosophies using different mathematics, yet both are converging on the same astonishing idea. The holographic principle has become a shared beacon in the dark, a point of profound confluence, suggesting that whatever the final theory of everything, looks like it will almost certainly be holographic in nature. This quest is not the work of lone geniuses locked in ivory towers. It is one of the most sprawling, collaborative, and intensely human endeavors in the history of thought. It unfolds in the hushed halls of institutes from Princeton to Cambridge, in bustling summer schools in the Italian Alps, and on late-night video calls connecting minds in Tokyo, Waterloo, and Stanford. It's a global conversation carried out in the universal language of mathematics. You will see cosmologists who spend their lives analyzing the faint light of the Big Bang, locked in passionate debate with string theorists who manipulate equations in 10 dimensions. You will see particle physicists from massive colliders like the LHC sharing data and insights with condensed matter physicists who study the strange quantum behavior of exotic materials here on Earth. The holographic principle has shattered the old silos of science. It has revealed that the physics of a black hole's event horizon might have deep connections to the behavior of superconductors, that the structure of the early universe could be linked to the entanglement of quantum particles. It is a unifying web pulling together the disparate threads of modern physics into a new and more coherent tapestry. On countless whiteboards across the planet, you will find the same equations, the same diagrams, the same tantalizing symbols representing the boundary and the bulk. There is a palpable sense of being on the precipice of a great leap, a feeling of shared purpose that transcends nationality and background. These scientists are modern-day explorers charting a territory that is not made of land or sea but of reality itself. They are driven by the most fundamental of all human impulses, the desire to understand, to know what the universe is and how it works. The experimental search for holographic noise and cosmic signatures continues pushing the boundaries of technology and precision. The theoretical work on quantum gravity deepens, guided by the principle's unerring logic. We have not yet found the definitive proof, the single, unambiguous piece of evidence that would allow us to declare with certainty that our universe is a hologram. The cosmic pixel remains elusive. The echoes in the primordial fire remain faint and contested. But the search has already changed us. It has given us powerful new tools, forged unexpected connections between different fields of science, and sharpened our questions about the ultimate nature of reality. The hunt for the physical edges of our universe, for its ultimate resolution, forces us to look inward to question the very foundations of our own experience. As we strive to understand the container, we are inevitably forced to confront the nature of what is being contained. This is where the journey turns from physics to metaphysics, from the observational to the existential. The quest for evidence leads us to a precipice staring down into an even more profound and unsettling question. If we are living in a projection, a grand illusion woven from pure information on a distant cosmic screen, who or what is the projector? And so we arrive at the edge of the map. We have travelled from the crushing certainty of a black hole's singularity, that point of infinite density where all our known laws of physics collapse to the shimmering, uncertain boundary of the cosmos itself. Our journey was not one of light years traversed by starships, but an odyssey of pure thought following a single tenacious question that refused to be silenced. Where does the information go? It was a question born in the titanic, intellectual clash between Hawking and Susskind, a debate that seemed at first to be a niche problem for theoretical physicists, a subtle flaw in the otherwise elegant mathematics of the cosmos. Yet, as we have seen, that single thread, when pulled, did not simply mend a small tear in our understanding. It unravelled the entire tapestry. It forced us to confront the very nature of space, of time, and of the substance we call reality. The search for lost information led us to an idea so counterintuitive, so profoundly alien to our everyday experience, that it continues to echo through the halls of science and philosophy, challenging the core of our perception. The holographic principle, the idea that everything you see, everything you feel, everything you are, the unyielding solidity of the ground beneath your feet, the warmth of the sun on your skin, the unfathomable distance to the Andromeda galaxy, is merely a projection, a fantastically complex high-fidelity illusion encoded on a two-dimensional surface impossibly far away. We began with a paradox about incinerated encyclopedias and quantum states, and we have ended with the potential revelation that we are living inside a cosmic hologram. Remember the strange mathematical marriage of convenience we encountered, the ante-de sitter conformal field theory correspondence. It was here, in the abstract realm of string theory, that the principle found its voice. Maldaceno's duality gave us a Rosetta Stone for the universe, a precise dictionary for translating between two completely different languages of physics. On one side, a universe with gravity, a universe with depth and dimension, the familiar bulk that we seem to inhabit. On the other, a flatland of quantum fields, a world without gravity, living and breathing on the boundary of that higher dimensional space. The revelation was not just that these two descriptions were similar, it was that they were identical. Mathematically, they were one and the same. A complex gravitational problem in the bulk, like the collision of two black holes, could be recalculated as a far simpler interaction of quantum particles on the flat boundary, and vice versa. This was not an analogy, it was a discovery of a deep hidden symmetry in nature, a fundamental equivalence that suggests one reality can be fully described by the other. The implication is as staggering as it is inescapable. The three-dimensional world, with all its perceived depth and substance, might be emergent. It could be the holographic ghost of a simpler, flatter, more fundamental reality. What does this truly mean for us, for you? It forces a radical re-evaluation of what is fundamental. For centuries, we have been cosmic archaeologists digging down through layers of reality to find the smallest, most basic building blocks. We went from organisms to cells, from cells to molecules, from molecules to atoms, from atoms to quarks and electrons. We assumed that to understand the universe, we had to dissect it to find the ultimate indivisible particle, the final Lego brick of existence. The holographic principle turns this entire worldview inside out. It suggests that the fundamental reality isn't found by digging down, but by looking out to the boundary. It suggests that the most fundamental constituents of the universe are not particles at all, but bits of information. Planck pixels, each one containing a single binary choice, a yes or a no, a 1 or a 0, etched onto the cosmic event horizon. From this perspective, space itself is not the empty stage upon which reality unfolds. It is the product of the information written on the stage's walls. Locality, the intuitive idea that an object is only influenced by its immediate surroundings, becomes a clever illusion. Two particles that appear light years apart in our 3D projection could be right next to each other, intimately connected in the 2D code. The fabric of space-time, which Einstein taught us, was a dynamic, flexible entity, maybe woven from the quantum entanglement of these informational bits. The universe, then, is less a clockwork mechanism of particles and forces, and more a quantum computer processing an unimaginable amount of information. And we, along with the stars and galaxies, are its output. This idea ignites a cascade of profound, unsettling philosophical questions. If our reality is a projection, what is the projector and where is the screen? Is there a real world on that two-dimensional boundary? And if so, what would it be like to exist there? Is it a place in any sense that we can comprehend? Mathematics provide a framework, but they are silent on the brace, experience. They give us the blueprint, but not the feeling of living in the house. Consider your own consciousness, your sense of self. You feel you are a unified being, a singular locus of awareness moving through time. Your thoughts, your memories, your choices, they feel intrinsically times yours, times originating from within the confines of your mind. But in a holographic universe, where is that mind located? If your physical brain is part of the 3D, projection is your consciousness. Also, a holographic image. Could the intricate network of entangled information on the cosmic boundary somehow give rise to the subjective experience of being you? It is a vertigo-inducing thought. The very notion of free will, of cause and effect, becomes shrouded in ambiguity. If the entire timeline of the universe, past, present, and future, is encoded on a static 2D surface, is our experience of the flow of time just another part of the grand projection? Are we merely watching a pre-recorded film, believing we are its authors with every frame that passes? The holographic principle doesn't provide easy answers to these questions. Instead, it reframes them in a language so new, so strange, that we are only just beginning to learn its grammar. It tells us that our intuition, honed by millions of years of evolution to navigate a world of predators and prey, of thrown spears and falling fruit, is a hopelessly inadequate guide to the ultimate nature of reality. Our senses present us with a world of 3 dimensions of solid objects and empty space, but this might be a user interface, a convenient fiction that allows us to function, hiding the bafflingly complex code running underneath. Just as the icon on your computer screen is not the file itself, but a graphical representation that allows you to interact with it, so too might our 3D universe be a representation of a more fundamental informational reality we cannot perceive directly. Now, it is crucial to state that the holographic principle is not, as of today, a proven fact about our specific universe. It is a powerful, mathematically consistent idea born from the study of black holes and nurtured within the abstract world of string theory. We have found tantalizing hints in the cosmic microwave background radiation, subtle patterns in the universe's baby pictures that align with holographic models slightly better than with standard inflationary cosmology. But these are whispers, not definitive proof. The experiments required to directly test the graininess of spacetime, to find the pixels of reality at the Planck scale, are far beyond our current technological reach. They would require a particle accelerator the size of the galaxy or a detector of gravitational waves with impossible sensitivity. So you might ask, if we cannot prove it, what is its value? Why have we undertaken this mind-altering journey? Because its true power, its lasting legacy, may not depend on it being literally true. Its revolutionary impact is in the questions it forces us to ask and the new tools it gives us to explore them. The holographic principle has become a new kind of lens for physics. It has provided a concrete way of thinking about how quantum mechanics and gravity, those 2 great pillars of modern science that refuse to cooperate, might be unified. It has irrevocably changed our understanding of information. Before, we saw information as a description of a physical system. Now, many physicists are entertaining the radical possibility that the information times is times the physical system. The old mantra was, it from bit, the idea that physical reality arises from information. The holographic principle gives this idea a concrete mathematical foundation. It has become an indispensable tool in other fields of science. Physicists are using the holographic duality, that dictionary between gravity and quantum fields, to solve intractable problems in condensed matter physics, studying the strange behavior of electrons in superconductors by modeling them as miniature black holes in a higher dimensional space. The principle is being used to explore the deepest mysteries of quantum entanglement, suggesting that the very geometry of spacetime is stitched together by these strange connections. Even if our universe is not a perfect hologram, the idea has unleashed a torrent of creativity and progress, reshaping entire fields of research. It has served as a powerful guide, pointing the way toward a deeper reality, even if the final destination looks different from our current map. And so, we are left here at the end of our exploration, suspended between 2 worlds: the familiar, tangible world of our senses and the ghostly informational world suggested by the mathematics. We are left with a profound sense of humility and an even more profound sense of wonder. For centuries, we have looked up at the night sky and seen points of light in a vast emptiness. We have felt a sense of our own smallness against the backdrop of cosmic grandeur. But the holographic principle offers a different perspective, a new kind of connection. The next time you look up into the darkness, past the moon, past the planets, past the shimmering river of the Milky Way, and out into the intergalactic void, allow yourself to entertain this extraordinary possibility. Consider that you are not looking times out, times into a vast 3-dimensional space. Perhaps you are looking times in asterisk, in toward the center of a colossal 4-dimensional volume, and that everything you see, the distant quasars, the ancient galaxies, the starlight from ages past, is all part of an intricate projection on the walls of our cosmic room. The universe is not a container for us. The universe might be a message written in a language of quantum bits on a distant boundary, and we, along with everything we have ever known or loved, are a part of its reading. The quest for understanding will continue. We will build more powerful telescopes, more sensitive detectors. We will push the boundaries of mathematics and theory, forever seeking the ultimate nature of what is. We may one day prove the holographic principle correct, or we may find it was a beautiful but flawed stepping stone on the path to an even stranger, more elegant truth. But one thing is certain: the journey has forever changed our place in the cosmos. We are no longer just travelers through a pre-existing space. We are face to face with the astonishing possibility that the deepest secrets of reality are not hidden in the heart of a distant star or at the beginning of time itself, but are encoded all around us in the very grain of existence, on the boundary of everything. And the universe we thought we knew has become a ghost of itself, a magnificent shimmering hologram whose true nature we have only just begun to glimpse.